Welcome to this problem-solving session. Today, we'll be tackling LeetCode problem number 415, add strings. This is a great problem to practice string manipulation and arithmetic operations in coding interviews. Let's dive in and explore the solution together. In this problem, you're tasked with adding two non-negative integers that are given as strings. The challenge is that you cannot use built-in libraries designed for handling large integers, such as Python's int or Java's big integer. Additionally, you cannot convert the input strings directly into integers. Instead, you need to simulate the addition process digit by digit. The inputs to the problem are two strings, number 1 and number 2. These strings represent non-negative integers, and their lengths can range from 1 up to 10,000 characters. The output should also be a string that represents the sum of these two numbers. For example, if the inputs are number 1 equals 11 and number 2 equals 123, the output should be 134. Keep in mind that the focus is on manually performing the addition process, similar to how you would add two numbers by hand. The output for the first example is 134. To understand how this result is obtained, let's break it down step by step. First, we align the numbers by their least significant digits. Since number 1 is shorter, we pad it with leading zeros, making it 011. Now, we add the digits column by column starting from the rightmost digit. At the units place, 1 plus 3 gives 4. At the tens place, 1 plus 2 gives 3. Finally, at the hundreds place, 0 plus 1 gives 1. Combining these results, we get the string 134. This process highlights the importance of aligning digits properly and performing addition column by column. In the second example, the inputs are number 1 equals 456 and number 2 equals 77. To add these numbers, we again align them by their least significant digits. This means number 2 becomes 077, while number 1 remains 456. Starting from the rightmost column, the units place gives 6 plus 7, which equals 13. Here, we write down the 3 and carry over the 1. At the tens place, 5 plus 7 plus the carry of 1 results in 13 again. We write down the 3 and carry over another 1. Finally, at the hundreds place, 4 plus 0 plus the carry of 1 gives 5. Combining all these results, the output is 533. This example demonstrates how to handle carries effectively during addition. In the third example, the inputs are number 1 equals 0 and number 2 equals 0. Since both numbers are 0, their sum is straightforwardly 0. This highlights a trivial case where no computation is necessary beyond recognizing that the sum of two zeros is still 0. Looking at the constraints, it's important to note that both input strings will have lengths between 1 and 10,000 and will only contain digits. There are no leading zeros in the input strings, except in the case of the number 0 itself. Key edge cases include situations where one number is significantly longer than the other, scenarios involving multiple carries across digits, or cases where one or both numbers are 0. These considerations ensure your solution can handle the full range of inputs robustly. To solve the problem, we considered two main approaches. The first is the brute force method, which involves converting the string inputs into integers, performing the addition, and then converting the result back into a string. While this method is intuitive and easy to implement, it violates the problem constraints because we are not allowed to use built-in libraries for handling large integers. This makes it an invalid solution for this problem, despite its simplicity. The second approach is a manual digit-by-digit addition, which mimics how addition is done by hand. Starting from the least significant digit, or the rightmost character of each string, we move leftward, adding digits along with any carry from the previous step. Missing digits in shorter strings are treated as zeros, and the result is constructed in reverse order before being flipped to get the correct output. This approach respects the problem constraints and provides an efficient way to handle the addition without relying on integer conversion. Now let's break down the steps for the manual digit-by-digit addition. First, we initialize pointers at the end of both strings and set a carry variable to 0. These pointers allow us to process the digits from right to left. We then loop until both pointers have gone out of bounds and the carry is 0, ensuring we handle all digits and any remaining carry. Within each iteration, we add the digits at the current positions of the pointers, if available, along with the carry. The result of this addition is split into two parts: the digit to store, which is the remainder when divided by 10, and the updated carry, which is the quotient. These digits are stored in a result list. After the loop completes, we reverse the result list and join it into a string to obtain the final sum. This approach has clear advantages: it adheres to the problem constraints, is efficient with linear time complexity, and handles edge cases like strings of different lengths or the need for a carry. The trade-off is that it requires careful implementation of manual carry handling, but the overall complexity remains manageable. The manual digit-by-digit addition approach was chosen for several reasons. First, it fully adheres to the problem constraints by avoiding the use of built-in libraries for large integer handling. Second, it is efficient, processing each digit exactly once, which gives it linear time complexity. Third, while managing carries manually adds some complexity, the logic remains straightforward and easy to follow, making it a practical solution. Compared to alternatives, the brute force approach is invalid because it violates constraints, and a recursive approach, though possible, would require more stack space and be harder to implement cleanly. In conclusion, the chosen approach strikes the right balance between efficiency, simplicity, and compliance with constraints, making it the optimal solution for this problem. In this problem, we're tasked with adding two non-negative integers that are provided as strings. The result should also be returned as a string, and we can't use any built-in methods that directly handle large integers or convert strings to integers. The approach we'll take involves manually simulating the addition process, working character by character from the least significant digit to the most significant digit. To start, reversing both input strings aligns the least significant digits at the beginning, which simplifies traversal. For example, reversing 123 and 456 gives 321 and 654. Next, we initialize two pointers at the start of these reverse strings to help us traverse them. We also set up a carry variable, starting at 0, to handle sums that exceed 9. Finally, we'll use a result list to collect the digits of the sum as we compute them, building the result step by step. The next step is to perform digit-by-digit addition using the two pointers. At each position, we convert the characters from both strings into integers. If one string is shorter, we treat any missing digits as 0. The sum of the two digits, along with the carry, gives us the total for that position. From this total, we extract the new digit by taking the remainder when divided by 10, and we update the carry by performing integer division by 10. This ensures that any overflow is properly handled in the next iteration. The new digit is then appended to our result list. For example, if the reversed inputs are 321 and 654, at the first position, we add 3 and 6, giving a total of 9. With no carry, the digit 9 is added to the result. At the next position, we add 2 and 5, yielding 7, which is also appended. This process continues until all digits from both strings have been processed. After processing the aligned digits, we need to handle any remaining digits in the longer string. These are added to the carry if one string is longer than the other. If there's still a non-zero carry after all the digits have been added, it is appended to the result list. For example, if the final carry is 1, appending it results in a list like 9, 7, 5, 1. Once the addition is complete, the result list, which currently holds the digits in reverse order, needs to be reversed to reconstruct the number in the correct order. For instance, reversing 9, 7, 5, 1 gives 1, 5, 7, 9. This reversed list represents the final sum of the two input strings. This approach mimics manual addition, starting from the least significant digit and propagating the carry when necessary. Reversing the strings simplifies traversal, as it aligns the digits for easy addition. The carry ensures that the sums remain accurate even when individual additions exceed 9. Edge cases are handled by treating missing digits in shorter strings as 0, interpreting empty strings as 0, and appending any remaining carry at the end. The result list, which supports efficient appends, is ideal for collecting digits during the computation. The algorithm runs in O, max, n, m, time, where n and m are the lengths of the input strings, since we traverse both strings once. The space complexity is also O, max, n, m, as the result list grows proportionally to the length of the longer string. This makes the solution efficient and well suited for the problem constraints. Here, we begin by defining the addStrings function inside our solution class. This function takes two input strings, number 1 and number 2, which represent large non-negative integers. Since we're working with strings, we can't directly use arithmetic operations, so we'll process the digits from the least significant to the most significant. To do this, we initialize two pointers, I and j, to point to the last characters of number 1 and number 2, respectively. We also initialize a carry variable to handle sums that exceed a single digit, and an empty list called result to store the digits of our final answer. Next, we enter a while loop that continues as long as there are digits left in either string or we have a non-zero carry. Inside the loop, we extract the current digits from number 1 and number 2 using the pointers. If a pointer has gone out of bounds, we default the corresponding digit to 0. We then calculate the sum of these digits along with the carry. The least significant digit of this sum, obtained using the modulo operator, is appended to the result list. The carry for the next iteration is updated by performing integer division of the sum by 10. Finally, we decrement the pointers to move to the next digits in the strings. After the loop completes, all the digits of the sum will have been processed, but they are stored in reverse order in the result list because we appended the least significant digits first. To obtain the correct order, we reverse the result list and convert it back into a string using map and join. This gives us the final sum as a string, which is then returned by the function. By working with digits directly and managing the carry manually, this method ensures we can handle arbitrarily large numbers represented as strings without relying on built-in integer arithmetic. Here, we are implementing a solution to add two non-negative numbers represented as strings. Since we are dealing with strings and not integers, we need to process them character by character, starting from the least significant digit. To do this, pointers I and j are initialized to the end of each string. We also set up a variable carry to handle any overflow during addition, and a string builder to construct the result as we compute each digit. Inside the while loop, we check if there are digits left in either string or if there's a carry to process. For each iteration, we extract the current digits using the pointers, defaulting to 0 if the pointer is out of bounds. These digits are then summed along with the carry. The least significant digit of this sum is appended to the result using currentsum %10, while currentsum/10 updates the carry for the next iteration. Finally, both pointers are decrement to move to the next higher digits in the strings. Once all digits have been processed and the loop is complete, the string builder contains the result in reverse order since we appended digits from the least significant to the most significant. To provide the final answer in the correct order, we reverse the string builder and convert it to a string before returning it. This ensures the resulting string represents the correct sum of the two input numbers. To begin solving this problem, let's consider the first example where we are adding the numbers 123 and 456. Initially, we set up our variables, number 1 and number 2 hold the input strings, while I and j are pointers starting at the last indices of these strings, which represent the least significant digits. We also initialize carry as 0 and result as an empty list to store our intermediate results. In the first iteration, we extract the digits at the current positions of I and j. Digit 1 is 3 from number 1 and digit 2 is 6 from number 2. Adding these together with the carry, we get a current underscore sum of 9. Since this sum is less than 10, the carry remains 0, and we append the remainder, 9, to the result list. Finally, we decrement both pointers to move to the next most significant digits. Now in the second iteration, we are looking at the digits at the updated positions of I and j. Digit 1 is now 2 from number 1 and digit 2 is 5 from number 2. Adding these together with the carry, we get a current underscore sum of 7. Again, the carry remains 0 because the sum is less than 10, and we append 7 to the result, giving us 9, 7. Next, in the third iteration, digit 1 becomes 1 and digit 2 becomes 4. Their sum, 5, is appended to the result, which now becomes 9, 7, 5. At this point, both pointers are out of bounds, and there is no carry left. The final step is to reverse the result list and join its elements to form the output string 579, which we return as the final result. Let's take a look at another example where we add 99 and 1. Here, the initial setup is similar. Number 1 is 99 foot and number 2 is 1, with the pointers I and j starting at the last indices of their respective strings. The carry is initialized to 0, and the result list is empty. In the first iteration, digit 1 is 9 and digit 2 is 1. Their sum, along with the carry, is 10. We append the remainder, 0, to the result, making it 0, and update the carry to 1. The pointer I moves to the previous digit in number 1, while j goes out of bounds since number 2 only has one digit. In the second iteration, digit 1 is 9 from number 1, while digit 2 is treated as 0 because j is out of bounds. Adding these with the carry of 1, the current underscore sum is again 10. We append another 0 to the result, which now becomes 0, 0, and the carry remains 1. In the third iteration, both I and j are out of bounds, so digit 1 and digit 2 are treated as 0. Adding these with the carry gives a current underscore sum of 1. We append this 1 to the result, resulting in 0, 0, 1. Finally, we reverse the result list and join it to form the output string 100, which is returned as the result. In the final example, we add the numbers 0 and 0. The setup is straightforward with I and j both starting at 0, pointing to the only digits in number 1 and number 2. The carry starts at 0, and the result list is empty. In the first iteration, digit 1 and digit 2 are both 0, so the current underscore sum is also 0. We append this 0 to the result, resulting in 0. Since both pointers move out of bounds and there's no carry left, the final step is to reverse the result list and join it into the string 0, which we return as the output. To analyze the time complexity of that addStrings function, we observe that the dominant operation is the digit-by-digit traversal of the two input strings. The main while loop iterates as long as there are digits left to process in either string or if there's a carry. This means the loop runs up to max m n times, where m and n are the lengths of the input strings number 1 and number 2. Within each iteration, constant time operations take place, such as converting characters to integers, performing addition, appending the result to a list, and updating pointers. These O1 operations ensure that each loop iteration adds a constant amount of work. After traversing the digits, we reverse the result list, which takes O, max, m, n, time, and then join the digits into a final string, which also takes O, max, m, n. Therefore, the total time complexity is dominated by the digit traversal and is O, max, m, n. Now let's discuss the space complexity of the addStrings function. The primary contributor to space usage is the result list, which stores one digit per iteration of the loop. The maximum size of this list is max, m, n, plus 1, where the additional digit accounts for a potential carry in the final sum. This results in O, max, m, n, space. Other variables, such as carry, digit 1, digit 2, and current underscore sum only require constant space, O1. When we generate the final result string using .join, no additional space is required beyond the memory already allocated for the result list, as Python builds strings efficiently. Thus, the total space complexity is determined by the size of the result list and is O, max, m, n. Comparing this approach to a brute force or naive method highlights its efficiency. A brute force approach would involve converting both strings into integers, performing the addition, and converting the result back into a string. While it might still have an overall time complexity of O, max, m, n, the constant factors are larger due to the overhead of handling Python's arbitrary precision integers. Additionally, the space complexity of such an approach would also be O, max, m, n, due to the temporary space required for the integer representations of the strings. In contrast, the current approach avoids these conversions entirely, processing the strings directly and digit by digit. By eliminating the overhead associated with integer operations, this method is more memory efficient and operates with smaller constant factors, making it a better choice for this problem. Examining the best, average, and worst cases further solidifies the efficiency of this algorithm. In the best case scenario, both strings have the same length, and there is no carry propagation, but the time complexity remains O, max, m, n, because all digits must still be processed. In the worst case scenario, one string is much longer than the other, and a carry propagates through every digit. Even in this case, the time complexity remains O, max, m, n, since the carry is handled in constant time per digit. In the average case, where the strings have similar lengths and the carry occasionally propagates, the time complexity is still O, max, m, n. The proof of this lies in the fact that the while loop performs a constant amount of work per digit, and both reversing and joining the result are linear in the size of the result list. With space complexity also dominated by the result list, both time and space complexities are consistently O, max, M, N, making the algorithm efficient and reliable across all scenarios. When solving string-based number problems, there are a few common pitfalls to be aware of. First, ignoring input constraints can lead to unexpected errors. For example, failing to handle edge cases like empty strings, strings with leading zeros, or extremely large numbers can result in incorrect outputs or runtime issues. Always validate your inputs and explicitly handle edge cases. Another mistake involves directly converting strings to integers for large numbers. In some languages, this can lead to overflow or performance issues if the numbers are too large. A better alternative is to process the strings character by character or digit by digit. Additionally, incorrect handling of carryover during manual digit-by-digit addition is a frequent source of errors. If you forget to propagate the carry correctly, your final result may be off by 1. Finally, reversing strings is often necessary for these problems, but reversing them improperly or forgetting to reverse them back can lead to incorrect results. Be sure to double-check your string manipulations to avoid these mistakes. Another common issue is failing to properly format the output. Many problems require results to be in a specific format, such as removing leading zeros. Even if your logic is correct, improper formatting can lead to incorrect outputs. Use string manipulation functions to ensure your results are formatted as required. Now, when it comes to interviews, there are a few key insights to keep in mind. Recognizing patterns is crucial. Many string-based number problems are effectively simplified versions of traditional arithmetic operations. Breaking them into smaller subproblems, such as managing carries or adding individual digits, can make them more manageable. Optimization is also important. While brute force may work for small inputs, interviewers often look for solutions that handle large inputs efficiently. Testing edge cases is another critical skill. Be prepared to handle scenarios like empty strings, single-digit inputs, numbers with leading zeros, and strings of vastly different lengths. Finally, always analyze the time complexity of your approach. For example, a typical digit-by-digit addition runs in O, max, N, M, where N and M are the lengths of the input strings. This not only demonstrates your understanding but also highlights the efficiency of your solution. There are also several related problems that you might encounter, which build on similar concepts. For instance, in the add strings problem, you're tasked with adding two non-negative integers represented as strings without relying on built-in large integer libraries. Another example is the multiply strings problem, where you'll need to multiply two string-based numbers and return the product as a string. The string-to-integer problem, often referred to as étoile, involves converting a string into an integer while handling edge cases such as invalid inputs, leading or trailing spaces, and potential overflow. Finally, the valid number problem focuses on determining whether a given string represents a numeric value, which might include integers, decimals, or even numbers with exponents. Familiarizing yourself with these problems can help you recognize common patterns and strategies for solving them. When it comes to alternative approaches, there are several methods worth considering. One is digit-by-digit iteration, which provides more control over carry management and runs in O, max, N, M than time. This method is particularly useful in constrained environments or when working with languages that lack support for arbitrary precision integers. Another approach is using built-in data type conversion, which is simpler and faster to implement. However, it may fail for extremely large inputs in some languages. This method runs in O, N plus M, time and is best suited for scenarios with lenient input size constraints or during prototyping. Lastly, recursive addition, which follows a divide-and-conquer strategy, can be an elegant solution. It handles carry propagation automatically through recursion, but it comes with the risk of stack overflow for very large inputs. While its time complexity is still O, max, N and M, it's more useful for demonstrating knowledge of recursion rather than being the most practical choice. Choosing the right approach depends on the specific requirements and constraints of the problem you're solving. Great job following along. In summary, we tackled that add strings problem, practiced string manipulation, and reinforced the importance of edge case handling in algorithms. Remember to practice similar problems to strengthen your skills. Thanks again for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!